All right, in general, a first degree or linear equation in one variable is any equation that can be written in the following form, and that's the standard form that's shown as ax plus b equals 0. Clarification, couple things. When we say this form, we mean a and b are numbers of some type. So we've got a single variable. It doesn't always have to be x, but we're going to refer to x in this case. But the bigger qualifier is this equals 0 piece. So if we can write something in this form, we can define it to be linear or first degree. Now, first degree itself refers to the exponent. So if you look at the x, you don't see anything there, do you? By design, we assume that it's degree 1 unless we intentionally write something else there. So if we mean a different degree, we will definitely say it in the example. Okay, so here's an example of a linear equation that is not in standard form, but you can imagine if we were to say distribute here or move this variable, this fraction over, maybe add 5 to both sides, that we could actually get this to look like this right here. So that also would be considered linear, even if it doesn't start off that way. So again, if we can write it in standard form, then we call it a linear equation. Now, what are we allowed to do when we're solving for an equation? Well, we're going to start with two rules that will eventually branch out and look at more complicated scenarios, but we initially are allowed to add or subtract as long as it's to both sides. Additionally, we're allowed to multiply or divide, again, as long as it's to both sides. All right, our first task in solving this equation is to look at what we can simplify in each side separately from each other. So on the left side, for example, I see this part right here, that minus 3, and I can actually go in and distribute that into both terms in the parentheses. Similarly, I can take that 3 and multiply that in. So that's kind of my first starting plan. So I'm going to keep the 8x the same. So minus 3x. And then minus 3 times minus 4 is plus 12. And then over on the right side, we have 3x minus 12 plus 16. Okay, now our strategy is to combine like terms on the same side. So I see an 8x and a minus 3x, so together that gives me a 5x plus 12. And then on the right, I see a minus 12 and a plus 6, so together 3x stays the same, so that's minus 6. Okay, so now I've got it simplified, so I've got variables on both sides and numbers on both sides, and so I just need to pick a side. I need to label or decide where I want to move all the variables and decide where I want to move all the numbers. One easy way to keep it straight is to label. So I'm going to put all the variables on the left and the numbers on the right, and you don't have to do it that way. You don't have to pick those sides. It's just organized in your sock drawer. It just helps to be consistent. So if on the left side I want all the variables there, that means I don't want the 12. So I'm going to subtract 12 from both sides. And, okay, so that gives me 5x equals 3x minus 18. And then I want the 3x to move over because I've decided all the variables need to go to the other side. So we're going to subtract off 3x, and that gives me a 2x here and a negative 18. Okay, so I have 2x equals negative 18, and I'm trying to isolate out the x, so how do you get rid of multiplying by 2? I'm going to divide both sides by 2. So I get x equals negative 9. And there is our solution. Yay! All right, in this next example, we start off with what are called two fractional terms. So we've got the halves and the thirds. And so one technique that helps is called clearing the fractions. Let me write that out to the side. We're going to clear the fractions. And so the plan is to think of a number, come up with a number that we can multiply both fractions by that will essentially get rid of them. So is there a number that 2 and 3 happen to have in common? So one technique is to just make a list of multiples of 2 and go, well, 2, 4, 6, 8. And similarly make a list of multiples of 3. So 3, let's see, double 3 I get 6, triple 3 I get 9. And then I look for a number that they both have in common. So hopefully you recognize that if I multiply both sides by 6, that should cancel out the fraction. So I'm going to do that. I'm going to multiply the left side by 6, and then whatever I multiply the left side by, I have to multiply the right side by. Okay, so now that I've got that strategy in place, I'm going to distribute the 6 in on the left. So that's 6 times x plus 2 over 2 minus 6 times x over 3. And then on the right side, I just have 30 here. Now, interestingly enough, 2 goes into 6 3 times, and 3 goes into 6 2 times. So when I divide out those numbers, I then can, I'm going to simplify this before I distribute that in. Okay, so now I don't have any fractions at all, and I'm just going to distribute there. So 3x plus 6, minus 2x equals 30. And then I can combine like terms. So 3x minus 2x gives me x. Then I have that plus 6 equals 30. And then, so I want to solve for x, so I see that plus 6 is with it. So I'm going to do the opposite. So that's 24. And so that is our solution. Okay, in this next question or next problem, we're asked to solve for a particular variable. So we've taken numbers away from you, and we're asked to rewrite this thing. And so we're going to analyze this what's called simple interest formula, which we'll learn about a little bit later. Right now we're just looking at the variables and the letters, and we're going to manipulate them out. So in the original problem, this thing is set aside for a, so it's a equals p plus prt. And I'm asked in this first example to solve for r. So I want to rewrite this in terms of a variable that's buried inside one of the other expressions. So let me first copy this thing down. PRT. Okay. And so let's have what's called a game plan meeting. This first term, P, is being added to the PRT thing. So how do you get rid of adding? Well, subtracting. Okay, so at some point we're going to have to subtract by P. Then I notice that the P and the T that are right next to the R, if it's touching the variable, that means multiplying. So at some point I'm going to have to undo multiplication, which means I'm going to have to divide by P and T. Okay, so now I got two game plans. I'm going to have to subtract a P, and I'm going to have to divide by P and T. All right, so since we're undoing something, order of ops says normally you'd start with multiply and divide. This time we're going to do it a little bit reverse. So I'm going to subtract off this P. Now A is not a like term, so it's just A minus P equals PRT. And then we said we are going to divide by PT. So that's what that looks like. Okay, so putting it all together, we have that our friend R is equal to A minus P divided by PT. And that's good enough for now. We'll stop there. We don't need to separate out in two different fractions or anything like that. All right, then we're asked to come next door and solve for P. So A equal, I'm just going to copy it down real quick here. Okay, but now we got a different problem. Because now I'm thinking about this in terms of P, and I happen to see that there are two P's in two different locations on the same side. And so I have to think of an algebraic process, think of a way that I could pull the P out of those two terms. Oops, hold on, let me fix that. Okay, sorry about that. And so algebraically, what I want to do then is I want to not necessarily divide, but it is a process similar to division. I'm going to do something called factoring. So I want to factor out this p. Okay, now I'm going to do a little more detail than I necessarily need to, but I want to make a point with this as far as what I am doing here. So I am coming back in, and so I want to talk about why factoring is very similar to dividing. I claim that those two expressions, the top one and the one that I just wrote, are similar to each other. And the way I'm going to justify that is, imagine if I did go back in, I'm multiplying by p and I'm dividing by p. Well, if I cancel that out, I'm left with just p itself, which is the original problem there. And if I divide by p here and I multiply by p there, I'm left with the PRT. Okay? So anytime mathematically you're not sure if that's a valid thing that you can do, you can always just remultiply it back out and just double check that you can get away with doing that. Now, like I said, when we factor, we don't normally do this step. We don't normally do this process. But this allows us to see what happens next. So p over p is 1, and p divided by PRT divided by p, well, that divides out, and I'm left with RT. Okay? So normally we go from this step to this step in one fell move. But back when we originally learned how to factor, that whole divide thing was something that was emphasized a long time ago. All right, now, what's our goal again? Sometimes it helps to stop and go, what am I doing again? We are trying to solve for p, right? So I've got p times this expression, so I want to divide by that expression. And so I get a 1 plus RT equals p. And that's our answer in terms of p.